So, hello everyone. Welcome to the first session on Fourier series. Yes, obviously the prerequisite to learn the Fourier series. Now, the prerequisite of a Fourier series is much similar to the Laplace transform only. The first point that you should remember is a seven trigonometric formulae, seven trigonometric identities that already you used in Laplace transform. So same trigonometric identities again we require in Fourier series. So and again in the same way. So whenever we come across the multiplication of trigonometric function, say cos square theta, okay, sine theta cos theta, okay, or cos a cos b, this way. So in such a case we have to convert that multiplication into the addition so that we can easily integrate it. So the main formulas in Fourier are about integration. So to get the integration, we convert cos square theta as 1 by 2 times 1 plus cos 2 theta, sine square theta as 1 by 2 1 minus cos 2 theta, sine cube theta as 1 by 4 times 3 sine theta minus sine 3 theta cos cube theta, and similarly sine a cos b, cos a cos b. So these 5, 6, 7 are mainly the important formulas. So most of the cases we require the formulas that I tell you, which are very important formulas. This 5, 6, 7, 5, 6, 7. These are the most important formulae. Along with that, 1 and 2 only. So 3 and 4 rarely required. So 1, 2, 5, 6, 7. These are the 5 identities mainly. They are most important in Fourier series. So that about the first part. I will not go in the detail now. So you should remember these 5 trigonometric identities so that you will convert the multiplication of a trigonometry to the addition. Okay, that about the first thing. Second, which is a very important rule that mainly we require in Fourier series, because whenever we come across a biparts, and in that biparts one of the function, you'll observe one of the function is algebraic. So whenever one of the function is algebraic, other is a trigonometry there, other is exponential, so we will not worried about that. So whenever one of the function in the multiplication is algebraic, in such a case we use this generalized rule of integration by parts. When to use generalized rule of integration by parts, which is integration uv dx, whenever this u is algebraic function, whenever this u is algebraic, okay, algebraic, then only we use this generalized by part. And what is the benefit of generalized by part? We can get that integration in a single line. Otherwise we have to apply simple by parts again and again till the derivative of that algebraic term becomes a zero. So you'll observe what is generalized by parts. Integration uv dx is u v1 minus u dash v2 plus u double dash v3, and so on. So here is alternate plus minus sign is there. So here this next sign, okay, so obviously this next sign is a minus only here. Okay, so u v1 minus u dash v2 plus u double dash v3. If you want, next is a minus u triple dash v4, and then plus so on. Okay, that way. So this is the rule that we have. So alternate plus minus. So what is this dash? Dash indicates the derivative. So u is algebraic function, say x square. So if this is x square, we have u dash as a 2x, u double dash is a 2, u triple dash is a 0. So obviously we no need to write the higher order terms now, provided u is algebraic. We get some finite derivatives, and after that we have to stop the writing these in finite terms. So what about v? V is the second function other than algebraic. So its integration we require. V1 is integration v dx, v2 is integration of v1 dx, and so on. So you'll observe the two of the examples shown here. Two of the examples are shown here by generalized by part. For your understanding, I will take two more here. So let I take a new example. Say we have to integrate say x square and cos nx, x square cos nx dx. Remember, the first function is algebraic. Yes, hence we can apply the generalized by part. So that generalized by part starts with, see here, we just denoting this as a u and this as a v. And the formula starts as u v1 minus u dash v2 plus u double dash v3 minus u triple dash v4 and plus so on. So this is the formula. So in this formula, if you start to write these values, now u is x square as it is we are writing, better to keep the bracket. Then v1 is integration of v, so integration of cos nx is a minus sin nx. Don't simplify these signs, keep as it is, because we're writing the generalized by part and we require next time v2, and v2 will be the integration of this first bracket because this bracket is v1 now, minus u dash. Now what is the derivative of u? That is x square, it is a 2x, this is u dash. So v2 is integration of v1, so integration of this bracket, so integration of minus sin nx. So I forgot it one thing, so integration of cos nx is a minus sin nx upon n, don't forget it. So integration of minus sin nx upon n is now minus cos nx. Is it correct? First, the integration of cos nx is a plus sin nx upon n. Integration of now sin nx upon n is a minus cos nx upon n square. So this is minus now here. So that about this is a u v1 minus u dash v2 plus u double dash. Now derivative of 2x is just 2, and we have v3. Now integration of minus cos nx become minus sin nx upon n cube, and that is the end of integration. This type of integrations we require. We here just integrated. We integrated x square into cos nx. Okay, exactly similar way we can integrate the other, just like x cube. This x cube e raised to 2x. That is another example shown here. This one is a u. This one is a v. X cube e raised to 2x dx is this one is a u. This one is v1. Okay, just a minute. So one is a u, other is a v1. Just one minute. So yeah, this one is a u, this one is a v1 minus u dash. This is a v2 plus u double dash v3 minus u triple dash v4, that way. Now you will observe u triple dash is a 6, so u fourth derivative is 0, so not written there. So this, remember, generalized by parts. Many of the examples of a Fourier series you can do with the help of generalized by parts. So this is one of the important prerequisite, very important prerequisite of a Fourier series. So that about the second point. Come to the third here. Now there are a few more integration formulas which are very simple. We already use in Laplace also. So that we require again here. So the formula integration of e raised to x is e raised to x upon a plus c. Integration of x raised to n is x raised to n plus 1 upon n plus 1 plus c. Now next two are important, integration of e raised to ax sin bx and e raised to x cos bx. These are very important formulas again. Example 4 and 5, they are important. These are important. They require number of times in Fourier series again. And again, we already use this formula in Laplace. So integration of e raised to ax upon sin bx is, if I take third formula here, the formula comes as a e raised to ax upon a square plus b square a sin bx minus b cos bx. This is the formula you should remember. And similarly, integration of e raised to ax cos bx is a e raised to ax upon a square plus b square a cos bx plus b sin bx. So these two are very important formulas again in uh, Fourier series. Remember, in Fourier series, half of the examples you can do with this generalized by part, and half of the examples you can do it by this second formula, e raised to x sin bx. So this type of integrations will come again and again there. Okay, so these are very important prerequisites that you require. Next thing what you should know is some fixed values of this trigonometric function. Yes, you already know few of the values like sine 0. if you say sine of 0, sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is a 0, and so on. So if these values you know, so these are general results. Suppose n is an integer, so in general sine n pi is always 0. Remember, sine n pi is a 0. Sine 2n pi is also 0. Sine of 2n plus 1 pi is again a 0. So majority of the times whenever sine terms comes, we get these benefits, and we get little simplified answers. We'll come to that while solving the example. So these values you require. So sine n pi, sine of 2n pi, or sine of 2n plus 1 pi, all these are zeros. But that is not a case for cos, because we already know this cos of 0, cos of 0 is 1, cos of 1 pi, that is minus 1, cos of 2 pi, cos of 2 pi is a plus 1, cos of 3 pi is minus 1. So alternate, cos of 4 pi is plus 1. You will observe when the suffix of cos pi is odd, that is cos pi, cos 3 pi, cos 5 pi, they are minus 1. Okay, they are minus 1. But whenever the suffix is even, say cos 0, cos 2 pi, cos 4 pi, cos 6 pi, that is plus 1. So in general, cos of n pi, cos of n pi is a minus 1 raised to n. Cos of n pi is a minus 1 raised to n. You will observe when n is even, it become plus 1. When n is odd, it become minus 1. So cos n pi value, always remember, it is minus 1 raised to n. Cos of n pi is minus 1 raised to n. But cos of 2n pi is plus 1. Why? Because for whatever n is integer, 2n is always even. If 2n is even, cos 2n pi is plus 1. And cos of 2n plus 1 pi is always a minus 1. Because 2n, for n is integer, 2n plus 1 is odd number. For n is integer, 2n is an even number. So cos values are very important values that you have to replace it carefully. So when cos n pi comes, it is minus 1 raised to n, but cos 2n pi is a plus 1, cos 2n plus 1 pi is a minus 1. That about some fixed values of this trigonometric function that we require. And lastly, a last prerequisite that we require is a concept of even and odd function. This concept of even and odd function, remember, this require only some few particular types of example where the interval of a Fourier series is either minus L to L, or in particular it is minus pi to pi. So value of L is pi here. So in general, if it is minus L to L or minus pi to pi, so minus L to L means minus 3 to 3, minus 5 to 5, minus 1 to 1, like that. So whenever the intervals are, say, minus L to L type, we use the concept of even and odd function. And the benefit that we get is half of the Fourier coefficient directly we can write it as a 0 with the help of this. We'll come to that later on, okay, in the examples. But what is even function and odd function? Yes, that you should know. So the even function is a function uh, where only even power of x appears. So x square is there, x square plus x raised to 6 is there. So whenever only even powers of x appear in the equation, we say that is even function. So x square is even function, x square plus x raised to 6 is even function, cos x is even function. Why cos x is even function? Because we know the series for cos x, the series of cos x is 1 minus x square by 2 factorial plus x raised to 4 upon 4 factorial minus so on. So cos x contains only even power of x. So it is a cos x is even. Mod x is also a even function. Mod x is also the even function. We'll come to that. Why it is even? Actually, the graph of mod x is symmetric about y-axis. So the graph of a even function is symmetrical about y-axis. Symmetrical about y-axis. And mathematical condition is also there. Whenever f of minus x is equal to fx, whenever f of minus x is equal to f of x, the function is even. Function is even. So I will show you the graphs of this function. Okay, wait for that. Next is odd function. Now, how to identify it is odd function? First of all, f of minus x comes minus of fx. So minus comes outside. Then it is odd function. Mathematically, f of minus x is a minus fx. That is one criteria to identify. Or the second criteria, the graph of this odd function is symmetric about origin. Means it is symmetric in opposite quadrant. whatever graph we get in first quadrant, same graph we should get in third quadrant, then it is odd function. Okay, if we have the graph in second quadrant, so same graph should be exist in fourth quadrant, opposite quadrant. It should be in opposite quadrant. That is odd function. Now, but the simplest way to identify the odd and even function is their powers. So already we say here, the odd function have the odd powers of x only. You will observe x cube, x5, x raised to 7. So as the x raised to 1, nothing is there means x raised to 1. So 1, 3, 5, 7. So these are odd powers of x, so it is odd function. Tan x and sin x are also the odd function because if you see their Maclaurin series, they will contain only the odd powers of x. Okay, odd power of. So the simplest way to identify even and odd function is whenever only even power of x is there, it is an even function. Whenever only odd powers of x is there, it is an odd function. So that way. So that about the identification of even and odd function. But remember, there are few functions which are neither even nor odd. So here x plus x square, actually x is an odd function, x square is even. So it is odd plus even, so it is neither even nor odd. Or we can say it is both even and odd together. So sin x plus cos x is neither even nor odd because it contains odd term plus even term. So in such a cases, we do not get the simplified value. So that is one more thing you should note down. And here are the graphs. So already I told the graph of even functions are symmetric about x-axis. So this is an even function. G of x is x square is even function. So you'll observe this g of x graph is here. This is the g of x graph because it's a symmetric about y-axis. While while if I say you that this x is just a minute, I'm not corrected. I want to take another color and not taken. So take it. Why is it not changing? Okay, forget it. So here is a fx equal to x, that is odd function, and you will observe the graph is in first and third quadrant. So here is one of the branch. Let I draw this. So here is the graph of y equal to x, and this is the graph of y equal to x, and that is the this graph exists in first and third quadrant. It is in both opposite quadrants, hence it is odd function. No need to draw the even plus odd function, which is x plus x square, is neither symmetric about y-axis nor symmetric about opposite quadrant, that way. Okay, so that about concept of even and odd function. And lastly, if you see here, these are the important results again. If fx is even and gx is odd function, remember this multiplication of even into odd is odd. Okay, but even into even is even. And lastly, odd into odd is even. You can correlate it with the signs also. Consider consider this even function as a plus and odd function as a minus. Okay, even function as plus, odd is a minus. So when we take plus into whenever plus number into minus number, the result is minus number. Means even into odd is odd, even into odd is odd. Next, plus number into some plus number, plus into plus is plus. That means even into even is even. But if we have minus number, negative number into negative number, so minus into minus is a plus. So odd into odd is even. So that way. So plus is like a even function and minus is like odd function, and you will get that. So here are the examples. So x square is even, cos x is even, both are even, their multiplication should be even. X is odd, sin x is odd. So odd into odd is even. So hx, this hx resulting function x into sin x should be even. Okay, and lastly, this x square is even, sin x is odd, and even into odd is odd. So final resulting function, that hx should be odd. So that are the concepts that you should remember. And what is the benefit now? The benefit you will get by this last formula. This is the most important formula that you have. Whenever you come across integration minus a to a, it is like minus L to L fx dx. Okay, minus L to L, minus pi to pi, minus A to A, fx dx. You can always take it is a 2 times 0 to A, 2 times, because it is a even function. It is even function. But whenever it is an odd function, integration minus A to A, fx dx is 0. So this is very important. This is a very important, because whenever we have minus A to A, fx dx, it always goes to the 0, and we can get few of the Fourier coefficient directly as a 0, and that is a benefit we get mainly. And because of that, this concept of even and odd is very, very important. That will reduce your work in the exam. You can directly able to say the value of few of the Fourier coefficients are 0. So integration minus A to A fx dx, integration minus A to A fx dx is a 0 there, so that you should remember. So integration minus A to A sin x dx is 0, because sin x is odd function there. Okay, so that about the prerequisite of a Fourier series. If you are good in these, if you understood these, definitely you can easily get a very good marks in a Fourier series. Okay, so thank you.